Okay, we're going to consider what we call the expected value of a random variable, or the mean. And essentially this is what you would expect to happen. So for the example of the pocket money, this was the distribution we saw before. I'm going to think about what we would expect to happen if we were going to roll the dice 60 times. What would we expect the mean amount of pocket money to be? So if I think about it, if I roll the dice 60 times, I'd expect to get a number 1 10 times. I'd expect to roll a number 2 10 times, number 3 10 times, and so on. Now I realise that that isn't going to happen every time, but that's what I would expect it to average out to be. So to work out the mean, I would work out the sum of all of the rolls, so 10 1s, 10 2s, 10 3s, 10 4s, 10 5s, and 10 6s, divided by the total number of rolls. And this would give me the average. You can work out the answer if you wish. But what's more interesting is that this calculation is the same as this one. If I look here, the 10 over the 60 is 1/6, the 10 over the 60 is 1/6, 10 over 60, 1/6, and these, of course, are the probabilities that were associated with each of these particular values for the random variable. So what I can see is going on is that to work out the mean, it's the probability multiplied by the value plus the probability multiplied by the value throughout. So I'm just going to sum up the probabilities times the value of the variable throughout. So if I work out this, I can double check, of course, that this answer comes to 3.5. So I'm left with the formula that the mean, or the expected value of the variable, this is notation we're going to use quite a lot, is given by the sum of x times the probability. And it's probably interesting to note that this is similar to the formulas that we've seen for mean before. We've seen before that the mean is given by the sum of fx over the sum of the f's. Well, in this case, if the frequencies correspond to probabilities, then of course x times the frequency matches the top. The sum of the frequencies, if they're probabilities, that of course equals 1. So the formula is very similar to the formulas we've seen before for the mean. That then extends to when we think about the variance of a random variable. And the formula for that is given here. And again, I'm just going to look at the similarities between the formulas we've seen before. Earlier on, we saw that the formula for variance is given by the sum of fx squared over the sum of f subtract the mean squared. But again, if the frequencies here are represented by probabilities, that becomes 1. The frequency becomes the probability, and I'm subtracting. Okay, I've got a different notation for the mean, but x bar and mu are both symbols for the mean. We'll talk exactly about how those are different again when we come to the option topic. But again, the formula for variance is very similar to the formula for variance that we've seen before. How does that work? In the case of just using those formulas to ease our calculations. So for the other example we saw before, we worked out the distribution in an earlier example. So I'm going to use these values now to calculate the expected value of x. First of all, E of x is going to be the sum of x times the probability of x. So it's a case of working this through. So 1 times 2/34 plus 2 times 5/34 plus 3 times 10/34 plus 4 times 17/34. And working that out, I'll leave you to do the calculations there. I think that comes out to be 55/17. I'll leave you to check that. For the variance, again, a case of applying the formula. This time it's the sum of x squared, probability of x, and subtract the mean squared. So I'm going to have x squared, so it's 1 squared times 2/34 plus 2 squared times 5/34 plus 3 squared times 10 over 34 plus 4 squared times 17 over 34. Subtract the mean squared. So subtract 55 over 17 squared. I'll let you do the calculation work. I think that comes out to be 239 over 289. I'll let you check that. An interesting aside here is that if I enter this into my calculator with this as x and this as p of x, if I put it into a list and then find the one variable statistics on this, then the number for here will be given by the mean and the number here will be given by sigma. Of course, this is the variance. The calculator will give you the standard deviation. So you just need to make sure that you square the calculator number to check that this is correct. But you can get these answers from your calculator by using that one variable statistics option. One last example, one application for these questions is games. And this is where we start to see a little bit of where probability is applied to games. Following situation, a fairground stall, if I roll a 6, I win $10. If I roll a 4 or 5 on a dice, I win 5, or 1, 2, or 3, I win $1. But it costs me $4 to play. So when I talk about X's winnings, I have to be careful, because whilst I win $1, that's really costing me 3, because I've paid $4 to play. If I win 5, that's really only winning $1, because I've paid $4. If I win 10, well, okay, I finish off $6 better off. Probabilities for these, of course, well, chances of me losing $3 are a half, or 3/6, 2/6 for that, and only 1/6 for that. So I've got my distribution for the winnings. So now it's quite easy for me to work out the expected value of these winnings. I'm just going to go through using the formula. It's going to be sum of x times the probability of x. I can do this. So it's minus 3 times 3/6 plus 1 times 2/6 plus 6 times 1/6. So I've got, what's this, minus 9/6 plus 2/6 plus 1, or 6/6. So helping me out here, 2/6, 8/6 minus 9/6, that's minus 1/6. So the expected value of x is minus 1/6. Done part 2. Question 3, is the game fair? Well, this value here tells me that the expected winnings for me are negative. If I play this game over a long period of time, I'm going to lose. So is the game fair? No. Why? Because the expected value of x, in this case, is negative. But if it was positive, it wouldn't be fair. It would be stacked in my favour. So really, the reason it's not fair is because it's not 0. For a fair game, I really need the expected value of x to be 0.